Okay, so the next idea we need is something that, again, is very intuitive. It's this idea of wave interference. Okay, so suppose that you have two sine functions here. So here's sine pi t, here's sine 2 pi t. And I'm going to draw the graphs together. All right, so this is, I guess this was orange or maybe it was yellow. But this is the sine 2 pi t, and the blue is sine pi t. Okay, so I've taken these two functions and I've graphed them simultaneously on the line. All right. Okay. Well, then what we can say is, well, actually, what if we added these together? All right. Now, when you add together graphs, the way that you do this, it's you pick one point on the x-axis here, and so I add the blue point to the orange point. Right. So if I pick the point here, I'd add this point with that point. And then that's going to give a new graph, right? It's going to give a new waveform that looks like this. All right. So this is the wave of sine pi t plus sine 2 pi t. Okay, and so this is known as wave interference because you're taking these two waves and you're interfering them in a way to give you a new wave. And just something to note here is you see where this hits the x-axis here, this is where y is equal to 0. So there's 0 wave here. So that's known as completely destructive interference. Right? That means that you had it would correspond to something like here where the high wave crest interferes with the low wave crest in the other one, and they completely cancel each other out.
And that's how you get from that line?
That's where you get with 0 here.
0.
Yes.
Okay.
And on the other hand, this is where you would have a spike. This would be constructive interference. You see the amplitude here is above 1.5, whereas each of these guys individually they're combined to 1. Right? So when you combine these things, you get a wave of greater amplitude. It's higher than 1. So that's constructive interference. Okay. Again, something we're really familiar with. Just if you go to the beach and you watch waves collide and you see shadows out in the water, that's all interference effects. Something to notice here is that this function itself is periodic. Right? It doesn't look like a sine function, but in fact it is periodic because you see you start, there's one cycle, and then it would repeat again. Oh. Right? So it's not obvious, but in fact, if you just carefully look at it, it's a periodic function. And so what we observe here is that when we add two periodic functions together, we get another periodic function. Okay? Now, is this a coincidence? Well, the general rule is the following, that if you have two signals, say f1 and f2, and if we divide their frequencies, okay, so divide omega 1 by omega 2, if it's a rational number, then f1 plus f2 will be periodic. Okay, so rational number, this is if it's not, if you can't really remember what that means, all that means is that you can write it as a fraction. Okay? So if their frequencies is a fraction of, like, say, 3 over 5 or 2 over 10, then their sum will be periodic. So here I give an example of this. So if you look at adding these guys, so here's one wave, here's another one. And so the frequency here is 1, and the frequency here is 3/2. Right? And so now if we look at this rule, if we divide 1 over 3/2, that's a rational number. That's 2/3, which is rational. So now, and in fact, if you can see this is definitely a periodic function. You can see the repetition. Okay. On the other hand, here we add two waves. So here the frequency is square root of 2 on this cosine, and here it's 3/2. So square root of 2 is an irrational number. It's a non-rational number. So if we look at this ratio, it's not rational. And in fact, this is aperiodic. Now you look at it and you might say, well, this looks fairly periodic to me. Right? It kind of looks like it's doing the same thing, but actually it's not. If you observe what's happening, the frequency is getting smaller and smaller. So the time it takes to go on one cycle is actually getting shorter as t gets bigger. So this is not a periodic function. Okay, and again, the reason is that if we look at the ratio of the frequencies, it's an irrational number. Okay. So a really nice application of this is something known as harmonics. All right, so do we have any musicians here? Yeah, very good. So you've probably heard of this term harmonics. What instrument do you play?
I play multiple instruments.
Okay, very good. Well, almost all instruments use this. In fact, all instruments do use this idea of harmonics. And harmonics are what gives different instruments their unique sound. And so the idea is the following, is that you start off with some, which we call a fundamental frequency. So here's like some baseline frequency. And now we take integer multiples of that frequency and we construct the waves. Right, so here this has a frequency of twice the fundamental one. Here's 3 times. Here's 4 times. Okay, so we can build up all these different what are known as harmonics. All right, and they're all obtained by taking one initial wave and then doubling the frequency, tripling the frequency, 4 times the frequency, and building up a collection of waves here. All right, and then what we're going to do is we're going to interfere these guys. So we interfere the harmonics, and that'll give us a new wave. And depending on the amplitudes of the individual harmonics, it's going to produce a unique sound. Okay? So this is actually how instruments differ, is that they differ in the amount of harmonics they have at a given frequency. So let's look at this in a bit more detail. So here's an idea. So here we have just sine pi t, and so this would be like your fundamental frequency of 1. And then here's your second harmonic here, because the frequency is twice as fast. Okay, so you have something that looks like this. All right. Now we can add these two together, and we would get something that looks like this blue curve here. Okay. So here we're just adding these guys, and the amplitudes are the same. It's f1 plus f2, and we're getting some new wave here. This is a combination of the first and second harmonics. But we also have the ability to change the amplitude of the individual harmonics. Right, so here what we're going to do is we're going to take the first harmonics 3 times as much, and we're going to take the second harmonic -2 times as much. So this -2 just means that it's going to flip the wave. Okay? But the point is that we're using these individual harmonics as building blocks. Okay? Mathematically, we describe these as taking linear combinations of the harmonics. And what you get now is when we add this 3 sine pi t minus 2 sine 2 pi t, we get a different wave. Right? So the main idea here, by changing the amplitudes of the harmonics, we can obtain different interference patterns. All right? So just using these two functions as building blocks, we can create a whole bunch of new functions by changing the individual amplitudes and then interfering them. Okay.
Start visualizing some of these ideas. So this is an app that was created by undergraduate students to allow us to, so in the past we used to do this in LabVIEW, but not everyone has a LabVIEW license. So we created a web app to be able to visualize some of these things. So the first thing in this app, there's a fixed frequency player. So it's going to play a note. So I'm going to play 440 hertz note. The first thing to do is turn down the volume. So you can hear that beep sound for 440 hertz. And what's shown at the bottom is what's known as the time domain representation. So how does the signal change as a function of time? So it's a single sinusoidal wave, and there are 440 cycles per second. The second way to look at the data is in the frequency domain. So looking at what frequencies exist in the signal. So in this case, there's just one frequency at 440 hertz. So if I play this, and then I start reducing the frequency, so I'm moving this to lower frequency, basically there are less cycles per second, and you get a lower sounding note. So it sounds more bass and less treble. And I think this goes down to about 27. Wow, that's a really strong bass. So that's the lowest it'll play. And then we can reset this, and we can play higher frequency notes. So as we increase the frequency, it goes to higher pitches, so more cycles per second. It kind of sounds like it's louder, but it's actually the same volume, just your ear responds differently to different frequencies. So we'll reset this. One other thing I should mention, the vertical scale on this axis is in decibels, so it's on a logarithmic scale. And a decibel, the idea is that, well, 10 decibels. So every 10 decibels means that it's 10 times louder. So the signal that we're listening to is at 0 decibels. If it were at -10, then that means it's 10 times weaker. If it's at -20, it's 100 times weaker. -30, 1,000 times weaker. So let me reset this and play this again. So this is at 0 decibels. This module allows us to listen to noise. So there are different types of noise. There's something called white noise, which means that there is noise at every part of the frequency spectrum. And basically, it's going to distort the signal that we have. So it sounds like static. You should be very familiar with that sort of noise. Now, for audio applications, or if you're sending data, you want to filter out this noise that's on top of your signal. So there are different types of filters. So one is called low pass. What it does is it allows the low frequencies to go through, and it attenuates these higher frequencies. So it sounds a little bit better, but it's still, you can still hear this background noise. There's also high pass frequency, and what it does, or filter, and what it does is it allows the high frequencies to pass through and the low frequencies get attenuated. So based on where the signal is, high frequency versus low frequency is more noticeable. So let me reset this. So there's also something called bandpass, and what bandpass does is it allows only a small band of frequencies to get through, so the low frequencies and the high frequencies both get attenuated. And if I decrease the bandwidth, it looks like that's the shortest I can get. It's just basically how many frequencies are getting through. So the single frequency player, the idea is that without any noise, you have a nice, clean sinusoidal signal, and you can see that it's represented by a single tone in the frequency domain. The second one to look at is the multi-frequency player. So I'm going to play a note. So this is a chord. So I'm pressing these keys on a keyboard or on a piano. Probably a more obvious thing so that you can see what happens when you add harmonics. So C4 and C5, they're a factor of 2 in terms of frequency with respect to each other. So C is at, my screen's in the way. C is at 263 hertz, and or C4 is at 263, and or 261, and C5 is at 523 hertz. And so when we play this, you can see that this is a periodic structure in the signal because I have a harmonic of the other signal. So I'm playing these two notes. This one is twice the frequency of this note.